Electronic waste has rapidly become a major environmental challenge. In 2022 alone, 62 billion metric tons of e-waste were generated. 48 billion tons of this were improperly recycled, representing an estimated $62 billion in missed economic opportunity. Containing up to 67 critical and precious metals, printed circuit boards, or PCBs, present a significant opportunity for recycling. However, the tightly integrated multi-material components make the separation process an incredibly challenging task. The current method involves either directly smelting the PCBs to extract their precious metals or smelting a shredded combination of PCBs and other electronics. Since 60 to 80% of a PCB's mass consists of plastic and fiberglass, most of the board is not recycled. Instead, it releases harmful pollutants, reduces the purity of the extracted metals, and increases overhead costs such as transportation and equipment maintenance. Under Volkswagen's Regenerate Plus sustainability strategy, the reduction of primary resource demand and the development of a robust circular economy have been identified as key sustainability priorities. With the company's commitment to decarbonization and the electrification of mobility, effectively recycling PCBs is becoming increasingly crucial. To address this, Volkswagen Group of America Innovation Hub, Knoxville, partnered with Neatco Engineering Services on a project titled The Circular Economy of PCBs. The goal of the collaboration was to develop an industrial process that separates PCB components with minimal damage and environmental impact. In the first phase of the project, a three-part process for removing PCB components was developed and tested. The process removed over 95% of a PCB's components with an 80% reduction in greenhouse gas emissions. In Phase 2, AI-based image processing networks were developed to extract crucial information from PCBs. These networks could provide detailed recycling data like the mass of recoverable materials, the locations of valuable components, and overall recycling grades for each board. Additionally, they offered geometric information such as size, shape, and manipulation points. In Phase 3, the AI imaging tool was taken a step further and incorporated into a robotic process. After identifying a PCB, the system would use the gathered information to choose an appropriate end effector and precisely move the board. In Phase 4, students at Conestoga College joined the project and built a prototype of an automated single-process component removal system. The system could remove the majority of components on selected PCBs and could even preserve the integrity of several component types for reuse. The next phase of the project is to integrate an additional AI vision system that sorts loose circuit board components for downstream processing. The project is actively seeking new partners who are eager to adopt and collaborate on these exciting technologies. Ultimately, the goal is to develop a scalable PCB recycling solution that will separate and sort components for further downstream processing. Once deployed, this system will add value to the recycling process by increasing the concentration and purity of recoverable resources, eliminating material losses due to non-targeted recycling processes, and reducing the transportation cost per output of usable end products. With each new phase, this project is moving closer to a novel solution for a circular economy. What opportunities could it create for you?